Alright, this is our first video for 11.1, Limits in Motion, the Tangent Problem, which is basically our introduction into calculus. We're going to do two major things in our introduction to calculus. We're going to look at what derivatives are and then what integrals are in the next section. So we're going to start today with derivatives. We're going to start with what seems like a pretty simple problem, just finding average velocity. So a little definition, average velocity is the change in position, or delta S, divided by the change in time, delta T. Uh, you could also call it change in distance over change in time. It's just position is used in our definition here. And S is the variable used to represent position. So if we're looking for the average velocity in example 1 here, when a car travels 120 miles in 2 hours and 30 minutes, that average velocity is going to be found by taking the the change in the distance divided by the change in time. The change in distance was 120 miles. The change in time is 2.5 hours. So 120 divided by 2.5, that's 48. So the average velocity is 48 miles per hour. But obviously that's the average velocity over that trip. We're not going 48 miles the entire time. To relate that to a more generic function, down below I just have this graph here, just some function with two x values a and b and two y values f of a and f of b. So if we are looking for the average rate of change, we are going to do the change in our position, which would be y, over the change in our time, which is x. And so basically what we're finding is slope, because our change in y would be taking y minus y, or change in position, if this did represent position and time. Then our change in position in the numerator would just be the same thing as our change in time. So I'd be taking, our change in y. So I'd be taking f of b, my second y value, minus f of a, my first y value. And my second x value, which is b, minus my first y value, which is a. So basically what I have here is our formula for slope that you've seen before, y minus y over x minus x, just using function notation. Now, the way that I have mine written here, this would end up being actually a negative slope because of the change in y going down. What we're really finding here is the slope of the secant line when we do this. So the average rate of change is geometrically the slope of the secant line. So what if we're interested in instantaneous rate of change? Well, and that's actually where we're headed down here in a second after we do a couple more examples. But when we're interested in instantaneous rate of change at one instant, let's say we're interested at the instantaneous velocity at time b, or that at that x value right there. So we want to know how fast is this object moving right at that instant right there. Well, what we need to do is find the change in y over the change in x, with these points getting closer and closer and closer. Like this one is actually moving towards this one, until they actually become, oops, I thought that was locked on there, until they actually become the same point. So really we're looking for there to be no change in that denominator, or we're looking for this to be 0 down here. Well, that's mathematically impossible. So that was where calculus basically was born, was in order to find how we could put 0 in the denominator and find an instantaneous rate of change. Okay, before we get there though, let's use that formula that we just have to find a couple of average rates of change here. It says a ball rolls unwrapped, its distance is s feet its distance s from the top of the ramp after t seconds is exactly t squared feet. So s equals t squared. S is the position. I'm just going to write this a little bit bigger. T is time, and the position is always equal to time squared. So that's basically our function. Our interval that we want to find the average rate of change on first is from 0 to 2. So in part A, we're going to be looking for the uh, average rate of change from 0 to 2. So from this point right here to this point right here. Okay? And if it's hard to tell, where that y value is, remember, there's the function. So the y value is 4 because t is 2. So we're really looking for the slope of that line right there, which I know we could compute right there graphically, but we want to use that formula above to kind of tie these pieces together. So we are looking for that velocity, that average velocity by taking delta s over delta t. So the change in s, I know we know our values, but I just want to remind us where these are coming from. This is coming from this formula s equals t squared. So in other words, it's going to be t squared. Actually, we're just going to do this. Let's put our values in right away. Uh, our second value for t is 2. So 2 squared minus our first value for t, which is 0 squared. And then I'm going to have my change in time in the denominator, 2 minus 0. I know you know that 2 squared is 4, but I'm just writing it this way so you can see how it's actually coming from that s equals t squared function. So this obviously would be 4 minus 0 over 2 minus 0, just 4 over 2 or 2, which is clearly the slope of that line. Up 4 over 2 is the same thing as up 2 over 1 or up 2 over 1. So the average rate of change from 0 to 2 is 2 feet per second. And the slope of that red line is 2. From 1 to 3, we have, here's the point at 1, here's the point at 3. Let's see, here's 4, 5, 6, 7, 8, 9 is right there, so that must be where this point is. I had to kind of piece this graph together so it doesn't look the greatest. But here's that secant line right there. Okay, so we're looking for the slope of that secant line, and we're relating this to velocity. So velocity, again, is change in s over change in t. Our function is t squared. S is equal to t squared, so we're going to have 3 squared minus 1 squared over 3 minus 1, or 9 minus 1 over 3 minus 1, which is 8 over 2, which is 4. Which, if we look at our slope here, our rise over run would be 8 over 2, which is the same thing as what I have written right there, which is 4. So the ball is moving at an average rate of change or an average velocity of 4 feet per second between the seconds of 1 and 3. And the slope of that blue line that I have there is also 4. So average rate of change, same as the slope of the secant line. Okay, now let's start looking into that instantaneous velocity idea. The instantaneous velocity is also known as the derivative. To find the ball's instantaneous velocity at any given time, we would actually be looking for the slope of the tangent line at that value. This value is known as the derivative, and it has other uses as well. So what we're looking for here is, let's say we were looking for the average rate of change, or excuse me, the instantaneous rate of change, not between 0 and 2 like we did before, but just at 2 right there. What would be that instantaneous rate of change? It'd be like we were trying to get those two endpoints to become the same point. Like we're trying to get that point to become actually that same point at the value of 2 comma 4. So that ends up giving us not a secant line, but a tangent line right there at that point. And do a very good job. Remember, a tangent line should really cross it at just that point right there. Okay. So if we want to find the instantaneous rate of change, we're actually finding that tangent line there. Um, so if I wanted to, I just wanted to throw this out there because this came up in class today too. If we were going to find the instantaneous rate of change at B, for example, in this graph up here, uh, it would be the same as the slope of that tangent line right there. If we were going to find it at A, the tangent line would actually look something like this. I'll make it a little bit better. There we go. Okay, now notice how it crossed the function right there. That's okay. We're just looking for the tangent line. If we zoomed in really, really close, we're just looking for the tangent line at that point. It might cross the function again somewhere else. Oops. It might cross the function again somewhere else, but it's okay. We're looking for it to be tangent at that value. So that's what we mean when we say tangent line. All right, so let's take a look at the uh, formula for the derivative at a point. This is the first of two formulas that we're going to get for this same calculation. If we want to find what's called f prime of A, which is also just the derivative of the function f at A, then what we're going to do is take a limit and let x approach A, where our x values are x and A. So the difference in my x values is going to be x minus A. And my y values then would be f of x and f of A. So what we're doing is saying, let's let x get really, really close to A. Okay, now let's say x was A. Let's say, we're saying it approaches, but let's say that x actually equals A. Well, can we put x, or a value of A in for that x right there? Well, no, we can't, because then we get 0 in the denominator. That's why we have to have limits. We have to let x approach A, and then we'll be able to, as long as the limit exists, we'll be able to find the derivative at that point, which is also the slope of the tangent line at that point. So if you got a ball rolling down a ramp, it's the same ball, same ramp, distance s from the top of the ramp after t seconds is exactly t squared feet. What is the instantaneous velocity of the ball after 3 seconds? So we're not looking for the secant line anymore. We're just talking about this point right here at a t value of 3. We know that the y value is 9. Here are the s value. We're looking for really the slope of that tangent line right there. We want to find the slope of that line, which is also the instantaneous velocity. So here we go. We're going to take the limit as, actually let's write this to start with. The derivative at 3 is what we're looking for. Would be equal to the limit as t approaches A. Now, I know in our formula we have x approaches A. In our problem here, we're using t for our independent variable. If you want to use x, it's really not a big deal. As t approaches A of, and actually what I'm going to do here is instead of using s, I'm going to go and use f. I think I did the same thing in class today too. So we want f of x, which is really our function. So I'll just put f of t minus f of A, which is, oops, I have an A there. I should have a 3 like that. That value should be the same as that value. So f of 3. And our denominator is going to be t minus 3. So let's find out what those are. So the limit of t minus, or of t approaching 3. And we have f of t. Well, that's just our function. That's the function t squared. F of 3, or really s of 3, would be, if I put 3 into the function, the y value I get is 9. So that's 9. T minus 3 is my denominator. So I have the change in y over the change in x. So it's like we're saying we have this value t here on the graph, on the y-axis, some value t, which obviously is what the axis represents, but we're letting that value approach 3. We want the value to get really, really close to being the same as the value 3. So one of our values, our x values is t, which means its y value is t squared. The other value is 3, which means its y value is 9. We're looking for t to approach 3. Well, I can't put that 3 in yet because I would still get 0 in the denominator, so that's no good. But if you notice, our numerator is factorable. So let's factor that numerator. This is going to become the limit as t approaches 3 of t plus 3 times t minus 3 all over t minus 3. These factors cancel out, and we now have the limit as t approaches 3 of t plus 3. And now, since it would not cause us to have 0 in the denominator, we can finally put 3 in. So this is going to equal 3 plus 3. We can let t be 3 now. So this is 6. That means that the slope of that tangent line right there is 6. This got kind of messed up when I printed it out. The slope of the tangent line at t equals 3, or at 3 comma 9, is m equals 6. So at 3 comma 9, the slope of that line is 6, which means that the instantaneous velocity is 6 feet per second at 3 seconds. Okay, so notice the difference here between these values that we found. We found up here two average velocities between 0 and 2, and then 1 and 3. And this one we found that instantaneous velocity at 3. All right, so now it wants us to find the not just the slope of that tangent line, it wants to find the equation of that tangent line. Well, for an equation, we need both the slope, which we know is 6, and a point. Well, the point that we have is 3 comma 9. So we can use point slope form, and we can put these in, our x and y values. Let's see here, 3, going a little fast. And we'll distribute that 6, and we'll add that 9 over and get y equals 6x minus 9. That's the equation of that line that is tangent at 3. All right, same ball, same ramp, same thing going on here. Want us to find the instantaneous velocity of the ball after 1 second. Pick a little bit better color here. So we know we're looking for the derivative at the value 1. So now we're looking for the limit as t approaches 1. This time I'm going to go ahead and just use our since our equation is s of t equals t squared, I'm going to use the s in our notation here. We're looking for s of t minus s of 1 all over t minus 1. So s of t is t squared. S of 1 means put 1 into the function. Well, that would give us 1. And our denominator is t minus 1. Okay, now just take a step back and realize that we are still just finding slope. Y minus y over x minus x. It just is with this limit. Oh, and I'm glad I said that because I just realized a mistake here. I haven't put the 1 in yet, so I still need that limit right here. What was I saying? Notice that we're just still finding slope. It's just that we want to find the slope where our x values are both 1. I'm looking for t to approach 1. I can't do that yet. I can't put that value of 1 in yet. But you notice again we have a factorable numerator. So we'll go ahead and factor that out. And get t plus 1, t minus 1. And the t minus 1s will cancel out. And we have the limit as t approaches 1 of t plus 1. And now we can go ahead and put that 1 in for t. And that'll give us 2. So the slope of that line there is 2, which means that the instantaneous velocity is 2 feet per second. And then it again asks us for the equation of that line there. Let's see, what point do we have? Well, actually, I have it right on the graph right there. The point is 1, 1. The slope is 2. We'll distribute that 2. We get 2x minus 2 and then we'll add that 1 over and get 2x minus 1. Which looks about right. If I continue that line right there, looks like it probably crosses at -1, right? All right, so we have one formula for the derivative at a point right there. There's your first derivative formula right there. There's a second derivative formula also used to find f prime of a, or the derivative of f at the point A. This time what we're going to be interested in is a value called h. And we're looking for h to approach 0. So before I do anything else, well, first I'll just put that we're going to have a big fraction bar. Before I put anything else, let me explain what h is. If I go back up to this picture right here, okay, remember we talked about trying to find the instantaneous velocity, so we'd be looking for these two, I lost it, so I'm just going to try to sketch that back in here real quick. Looking for these 2 points to actually become, this 2 x values to actually become the same value. We're trying to like pull this a over to make it the same thing as b, right? So what we're going to do is consider this distance from here to here to be h. And I didn't think it made sense to put this before because we had no h at all. So if we consider that distance between our 2 x values to be h, let's talk about h becoming 0. That's what this is. H is the distance between the 2 x values. So our denominator, which in a slope formula represents the difference in the x values, we want to be just h. Our numerator then, our 2 y values, which we're going to have to find the difference between, well, one would just be f of a. The other would be different, the x value would be different by an amount h, because remember we said h is the difference in the x values. So that means that the other one must be f of a plus h. Okay, let me write this with a little bit thinner mark here. F of a plus h minus f of a all over h. And if we let h be 0, that means that the difference in our x's is 0. And look at what it does to our y's. It would make both of our y's f of a. So the y's are the same, the x's are the same as h equals 0. So geometrically, this would be the slope of the tangent line. It is another formula that calculates the derivative of f at a. All right, before we go and use that formula, we'll use it on the back side of this sheet here. Let's talk about differentiability. Okay, because not every function is differentiable at every value of a. All 3 graphs that you see down here are, all 3 of them are differentiable at every point on the graph except for 1, and they're all not differentiable at 0. Okay, and here's why. Unless a function has a well-defined slope when zoomed in at a, the derivative will not exist at that value a. So the first one I want to point out is this one in the middle here. Let's say I ask you to find the derivative at 2. You don't have to draw this in here, but at 2, we're looking for the tangent line, the slope of that tangent line right there. Okay, we could do that, right? We could find the slope of that tangent line pretty easily. It's differentiable at 2. In fact, picture moving this value of x, around the graph. What would it do to that tangent line? If I had it here at 1, it would look like this. If I had it over here, if I was looking for the derivative at -3, then that line would look like this. Okay, there's one spot though where it would give us an undefined slope, and that's at 0. At 0, we would actually have this vertical tangent line. Well, a vertical tangent line, a vertical line, has no slope. The slope is undefined. So this function is not differentiable at 0. It's differentiable everywhere else, but not at 0. This function here, there's not a well-defined slope at 0. I could draw all sorts of different tangent lines if I could actually do it. So there isn't a definable slope at 0. So this function is not differentiable at 0. And this one is actually discontinuous at 0. So there's no way to find a tangent line at 0. So all 3 of these functions are not differentiable at x equals 0. They're defined at x equals 0. They all have a defined value at x equals 0. This one is 0. This one is 0. and this one would be uh, 1, because it says for x equals 0, y equals 1. So they're all defined at 0, they're just not differentiable at 0. All right, so now here are the two formulas we got then for finding the derivative at a point. We have f prime of a equals the limit as x approaches that value a. Our two x values are x and a, and our two y values then would be f of x and f of a. Or we have the derivative of a is equal to the limit, and now in this one we talk about the difference between our x values being some value h that we're going to let approach 0. So our denominator is h, and our numerator then, the difference in our y values would be f of a plus h and just f of a. All right, that's when we're looking for the both of those would find the exact same value, looking for the derivative of a function f at some point a. Um, our book made the note there. I don't know if you saw that this one is easier for computing. I think both are good in different ways. The blue one there is the one that we'll use more often because that's what you'll see more often in your calculus class. So this next one here says find the derivative at 4 of this function. Okay, that's what f prime of 4 means. Find the derivative of the function at 4. So we're looking for f prime of 4. 4 is our a value then. So we're looking for the limit as h approaches 0 of f, change my color here, f of, uh, we want a plus h, right? Well, a is 4. So 4 plus h minus, and then we want f of a. Well, a again is 4. So now let's think about what this means. This means put 4 into the function. Well, if you put 4 into the function, f of 4, I'll just write here kind of in the margin for this one, since this is our first one that we're doing with this formula. F of 4 actually equals 2 times 4 squared minus 3. Well, it'd be 16 times 2 is 32 minus 3. F of 4 is 29. So I know down on my next step here, I'm going to have minus 29. We're going to need a little bit more space than that. Minus 29 after that subtraction sign. Okay, I have h down here. All right, now let's find f of 4 plus h. Well, this means put 4 plus h into the function. So we're going to put that in for x. So we'll put that in for that x right there. So we've got 2 times 4 plus h squared minus 3. So there's 2x squared minus 3 when x is 4 plus h. And we're going to take the limit of that plus h approaches. I'll just keep working down here like this. All right, so in our next step, we actually need to FOIL out that green stuff right there. So we're going to have to FOIL out 4 plus h squared. Well, I don't know about you, but my brain works better if I picture this as h plus 4 squared. I know it's h squared plus 8h plus 16. But that's being multiplied by 2. We have that minus 3. And we have that minus 29 there, still chilling out at the end, waiting for us to get done with that green stuff over there. So we're going to distribute that 2. And get 2h squared plus 16h plus 32, but then we have to subtract that 3, so it's going to be plus 29. Well, look what happens here. Then we have that minus 29, and we know that those two 29s are going to obviously cancel out. So in our next step, we're gonna kind of do two things at once here. Notice also that in our numerator, since those 29s cancel out, our two constants cancel out, we have a GCF to pull out then. We can pull out an h in that numerator. If we pull an h out of that 2h squared plus 16h, we'd be left with 2h plus 16. Now, the h's cancel out. Since we don't have an h in the denominator anymore, we can actually Now finally, let h be 0. Make this look a little bit nicer. We can let h be 0. We can put that 0 in for that h. So when we do that, 2 times 0 is just 0, and we get that this equals 16. And actually, if you want to show, you know, what happened there, we put the 0 in for h because we can. It's not going to put a 0 in the denominator anymore. It's defined. So we get 16. So I don't know if this was talking about position and time, so I'm not going to call this an instantaneous velocity at all. I just know that f prime of 4, or the derivative of that function at 4, is 16. All right, so we're already at a half hour here. I think this is pretty much what we got through in most classes in the first day, so I'm going to stop here, and we'll finish the rest of these in our next video.